Okay, welcome everyone to the robust optimization webinar of this week. So I'm very happy to introduce Merve Bodur. She's associate professor in the School of Mathematics at the University of Edinburgh. So she moved there recently, and her main research is about optimization under uncertainty, with focus on discrete optimization and a lot based on or focused on a lot of applications from scheduling, transportation, healthcare, and many more. She serves as on the editorial board of three journals, the OR letters Omega and Infor, and she's the vice chair of the Informs Computing Society, and she serves as a on the committee of stochastic programming, and she's one of our webinar friends, has her own or is, co-organizing the stochastic programming webinar or seminar. I'm very happy that we can collaborate, and please, Merve.
Thank you very much, Yanis, for the kind introduction. And thank you very much to both of you, Yanis and Ahmed Reza, for first of all organizing for this wonderful seminar series and also for giving me the chance to present some of our recent work. And thank you very much for all of you for joining me today. So, by the way, please feel free to jump in any point during the presentation if you have any questions, if you want to discuss anything further, or if you want me to clarify anything before I go further. So today I would like to tell you a little bit about how we would like to solve, or rather we will see derive primal and dual bounds for multi-stage adaptive robust optimization problems. And we will do this by using these various types of primal and dual decision rules. And this is, first of all, let me introduce, we have a pretty Francophone team here. So this is a joint work with Meryem Daryalar from HEC Montreal and Ayşenur Arslan from University of Bordeaux, and me, at least for me, I can say maybe I learned French before English, so if it makes me a bit Francophone. All right, so let's get started. So we are gonna solve, at least we will try to address these multi-stage robust optimization adaptive problems. But this is, as you all know in this audience very well, this is a super complicated problem class to attack, not just from a theoretical point of view, but also from a computational point of view. And in fact, our perspective will be more on the computational perspective, but we will try to reduce the complexity of this terribly difficult problem class by collapsing it by restriction of the policies, or from the dual side, the dual decisions. We will collapse this multi-stage problem into a two-stage problem. So this will give us most notably two main advantages. One is the computational complexity will drastically be reduced. Two, computationally, we will be able to leverage anything that this community develops to solve two-stage robust problems, robust optimization problems. But if you know me, I am actually coming from stochastic programming background. So this is my home community, I would say. So in that regard, what we wanted to do in this work is also translate some of the recent ideas, especially with respect to these novel decision rules. We would like to translate these relatively successful recent ideas from stochastic programming literature to the robust optimization literature. So this is going to be our high-level game plan. So let's start with the overall sequential decision making under uncertainty framework. So we are given presumably in my talk, say a finitely many decision making stages. So at each decision making epoch, we are supposed to take a set of actions without knowing exactly how the uncertainty in the future will look like, right? We have a rough idea and we have a model of uncertainty maybe, but at every point in time, while we are making decisions, our decisions should be, first of all, only adapted to what we observed at the time of the decision-making epoch. So uncertainty will be in a gradual manner will be revealed to us as we make these decisions, but our decisions will be dynamically adapted to only what we observe. So if we are making a decisions at this point, only what we observe up until this point, as well as what we decided and implemented up until that point, our new set of decisions will be functions of those, not the future. So let's formalize our setup a little bit better for what I will call in short MSARO, multi-stage adaptive or adjustable, if you like better, robust optimization problems. So as I mentioned, we are going to focus on a finite decision-making horizon. We are given this T decision-making epochs, and I will be using this set notation with the bracket to denote the integers from 1 to whatever is given into the input to the brackets. So we have these probably like strictly more than 2 mini decision stages that we are interested in. And then there's, of course, uncertainty in the sequential decision-making framework. So what we will denote by is if we look at this stage, so this is our decision-making horizon, if we are at stage decision-making epoch T, the set of uncertain parameters associated with that stage will be denoted by this psi subscript T. So if this is a production planning problem, this is maybe the demands of certain types of products you have at period or decision-making epoch T. So this is vector. And if we put all of these vectors from the beginning of the horizon up to T, I'm going to use the superscript notation. This will denote all of the uncertain parameters associated with the decision-making process up to stage T, all of them together, the superscript. So then if I have T many stages, size superscript capital T is all of the uncertainty we are dealing with in this finite horizon problem. And we are doing robust optimization. So we have the uncertainty model most notably in the form of an uncertainty set, which is, in other words, the support of our overall uncertainty vector. So we will also be needing something as a helper here, that the projection of this uncertainty set for the whole uncertainty up to the stage T, I will be denoting by this support superscript T, because they will come in handy as we write the models. So in terms of the system dynamics, as we discussed already, this is a gradually decision-making under uncertainty. So if we are at this stage T, we would like to make some decisions given our most recent state of the system, of course, and the last set of observations regarding the uncertainty associated with stage T, and we will make the new set of decisions and roll the horizon and continue. But as I mentioned in the previous slide, our decisions can only depend on what we've seen before and what we implemented before, not anything from the future. So in that regard, our decisions must be what we call as non-anticipative. They cannot cheat and anticipate the future. So in that regard, if you are at stage T and you are making this decision vector xt, it can only be a function of history of the uncertainty that you observe up to this, remember, superscript notation. Right? So they cannot depend any uncertain variables that you will observe moving forward. So we have these non-anticipative decisions. So, but the most important output of this multi-stage robust optimization model would be the first stage decisions, which are deterministic. So for notational convenience, we can think of them as a function of the first set of random variables, but we will, for convenience, just assume they are fixed to a constant so that our first stage decisions, indeed as desired, they are deterministic. So in this work, we are especially interested in addressing, or at least coming up with some helpful ideas to attack multi-stage robust optimization problems with and without integer recourse. So we allow some of the recourse decisions, or first stage decisions, if you will, to have potentially integer values. So we might very well have integrity restrictions for some, if not all, of the decision variables in our problem. So as I said, please feel free to stop me if you have any questions at all. So let's now put this system into a mathematical model, a pretty standard, I would say, MSARO model, but rather than this nested min-max-min form, I'm going to give you a monolithic formulation of the whole multi-stage robust model. So I will do that by introducing this single decision variable, which is representing the worst case objective value across our finite T-stage planning horizon. So this is the total cost that we are trying to minimize in, if you will, in a stage T period, stage T problem. So what we have here is this guy is for every possible uncertainty realization. And remember, this is the whole sample path towards the future, right? So from beginning and to the end, this is a full realization of uncertainty, a particular one coming from this uncertainty set, or if you will, the support. So, but this could be, of course, an infinite set of possible realizations you might have. But suppose I'm writing this possibly infinitely many constraints here, saying that for every uncertainty realization, I look at my overall cost of my decisions under that particular realization. The z variable is going to be the maximum of those, right? This is the worst case outcome. So with respect to the constraints, of course, for every decision-making stage T and for every uncertainty history of uncertainty realizations we can observe, we will make a set of decisions. But with respect to feasibility conditions, we will distinguish them into these two sets, namely the state constraints and recourse constraints. And it will be clear shortly why we want to make this specific distinction. And actually, shortly, we will also do the similar distinction for our decision variables. So the state constraints, or sometimes they are equalities, or most commonly, I will say they are known to be state equations. So what we have here is why they are special is these are the ones including consecutive decisions from multiple periods. So both xt and xt minus 1, they are linked together in these set of state constraints, whereas the recourse constraints, they are written only for all t separately, so they do not mix and match different decisions from different stages. So in that regard, we have these state constraints and recourse constraints, but as I mentioned, we might very well have some of our decisions integer valued, so we have in general mixed integer recourse. But everything I'm assuming cost and constraints, everything I'm assuming linear form. I don't have nonlinearity in that regard. So this is our formal MSIRO model. And as we know from the literature, and especially there's very nice recent literature regarding the theoretical complexity of this problem class. Now we know with confidence that MSIRO models, actually, they are harder to solve than any NP-hard problem you can imagine. So they are lying in the much higher levels of the polynomial hierarchy. And more importantly, the computational theoretical complexity of these models, they increase with the number of stages, the capital T. So a two-stage adjustable robust optimization problem in that regard is much easier to solve from this complexity perspective than the MSIRO problem. That's why when we play our game here and we reduce MSIRO problems into 2-ARO problems, we will be drastically reducing the theoretical complexity of the models we need to computationally deal with. So for those of you who are watching this recording in the future, I really hope we are able to now solve the MSIRO problems. We can kill them. But at this very moment, I'm giving this presentation. Unfortunately, I should report that we are not doing that well yet to solve MSIRO problems exactly, let alone get very good primal and dual bounds. And especially the dual bounding side is much scarce with respect to the ideas out there. So this is what we will try to fill in a little bit in the literature. So this table is just giving you a high level of some people who are commonly contributing to the area, but this is by no means a comprehensive list. So I'm sure many of you in the audience have already made very valuable contributions. So I apologize for not having a full picture here because it's a very vast literature, as we know. But what I want to highlight here, a couple things quickly is, first of all, for two-stage adjustable robust optimization problems, we know much more. We have various very interesting valuable ideas, methodological ideas to address them, both from a primal perspective, to get primal policies and bounds, upper bounds for a minimization problem, but also to solve them, if you will, exactly to true optimality. But this is very nice. There are a lot of, especially even recent developments with respect to heuristic ideas, whatnot. But if you look at the broader MSIRO problem class, then with respect to solving them exactly, we have very limited options. And many of these works in this picture, actually, they do only address a very specific class of MSIROs. So you need to have a special type of uncertainty set form, a special type of recourse type, and so on and so forth. Like some coefficients should be, say, fixed, so on and so forth. But with respect to solving them exactly, we are at this current point of, yeah, there is not much hope at the moment, but I'm really hopeful for future. But with respect to the primal approximations, I will show you in the next slide. There are a bunch of ideas, especially some, most of them commonly using decision rule-based approximations. But I would like to highlight the fact that it is one of our main considerations in this work is if you have a primal approximation, you have a policy, you have an upper bound for a minimization problem, but because we don't know the exact solution, how can you argue that you have good enough policies? You need a dual bound to say that my optimality gap is small, so I have good enough solutions, right? So in that regard, dual bounds are extremely useful, and there are only few works, and I would say most of them are mostly helpful for MSIROs with continuous recourse, but we want to extend it and do something for general MSIROs with mixed integer recourse in this work. So what kind of common approaches you might want to pull up from the literature if you want to solve your special type of MSARO problem? You can choose to do approximations, or if you are lucky, you have a special structure, maybe you will pull and try some of the exact approaches. So for approximation's sake, if your model has MSARO model has continuous recourse, you can find a lot of decision rule based approximations, especially this is the one affine or linear decision rules is the one that I'm going to use in my talk shortly. If you have discrete recourse, of course, these decisions, LDRs or affine decision rules will not be appropriate, but there are some nice applications of piecewise constant type of decision rules, for instance. But there are also some other interesting and very, very practically relevant ideas. And again, some of you in the audience have significantly contributed to these ideas as well, like uncertainty set partitioning or k-adaptability. But as far as my experience goes, k-adaptability has been really, really helpful computationally to attack two-stage robust optimization problems, which we can immediately borrow in our framework as a helpful tool. I will show you shortly. So on the other hand, if you have again MSAROs with purely continuous recourse, there is one again plus bunch of other constraints, restrictions on the structure. You can consider either DP algorithm or one of the again maybe most successful things. If you are in the two-stage problem setting, you might consider constraint and column generation, which we basically test numerically in our work. So overall picture, what are we proposing in this work? So we want to solve, say, a minimization type of MSARO problem. Again, general structure, we don't have much of an assumption on the structure. We want to handle the mixed integer recourse most notably. So first of all, from the primal perspective, we would like to restrict the solution of this problem, the policy, by applying a certain type of decision rules, namely two-stage decision rules, not necessarily linear, and I will explain shortly what it is. But because we are restricting the policy, we will only be able to get a feasible solution and accordingly an upper bound to our original optimal value. But the good thing is we are, after applying these decision rules, we are reducing a multi-stage robust problem into a two-stage robust optimization problem. So depending upon the structure in this two-stage adjustable robust optimization problem, we can hope to solve it maybe exactly in finite time by CCG, or we can successfully computationally maybe get some good solutions via k-adaptability, or I think I saw Esther in the audience, NER2RO, and so on, right? Or you can also consider the recent, ideas to enhance CCG in that regard computationally. From the dual perspective, what do? We apply some decision rule restrictions to the dual multipliers. And what kind of duality we are using? We are using Lagrangian duality because we want to consider mixed integer recourse. We don't have necessarily linear programming type of a setup. So we are going to employ Lagrangian duality, and we will apply restrictions on the Lagrangian dual multipliers, which will reduce the multi-stage problem again into a two-stage. Actually, it is slightly different than this one, but it is a two-stage problem after all, and it will give us a dual bound. And for this one, in this work, we consider two cases. If you have purely continuous recourse, we show that this restricted dual problem that we are proposing, we can reformulate it monolithically as a bilinear program. So you can give it to Groby, for instance. And for the general mixed integer recourse case, we propose a cutting plane algorithm to solve this dual problem. All right, so now let's look into the first primal case, and then shortly I will move on to the dual case. So first of all, let me start with MSAROs with purely continuous recourse, and this idea which is very, very commonly employed in the literature, namely linear decision rule restrictions. So we look at our problem, right? We have a t-stage problem. At each stage t, we have this decision vector xt, which is parameterized by the history up until that point. So these are flexible policies, right? So this xt is a mapping from the history to a decision vector, but these guys are adaptive fully, right, to the observations of the uncertainty realizations. But in this LDR restrictions, linear decision rule restriction, what you do is you restrict all of these decision variables to follow a specific form, a linear or rather affine form of uncertainty they are parameterized with. So here's maybe a quick example. Suppose this is, I'm talking about again, maybe an inventory management problem. This X corresponds to how much I produce or how much inventory I keep. And these guys are all of the demand observations of my product up until that stage T. So what I do is I say this XT variable it is going to be a function of all my demands. So namely, I observe this demand at the beginning that I know, and these demand values. So we basically employ a linear regression type of restriction. You go ahead and you introduce a deterministic coefficient for all of these guys, and then say this xt, how much you are going to produce, how much inventory you are going to keep. It cannot be just any number. It has to be this affine function of the green size that you will observe. So you restrict these decisions. And you do this at every stage for every decision variable, but then what happens is this collapses this multi-stage problem into literally a single stage problem, where now your only decisions are these deterministic linear regression coefficients that you need to train your model and learn. But once you get these betas, the design parameters of this decision rule, if you will, or linear regression coefficients, then you just observe the uncertainty, you plug it into this formula, betas are decided at the beginning as here and now decisions, you know what to do. So there's no more further decisions to be made. So this becomes a one-stage problem. So this is from the literature. So you, again, apply this linear decision rule restriction to all of your variables in the multi-stage problem. But our proposition is inspired from our relatively recent work from the stochastic programming literature, is don't apply it to all of the variables. Apply this linear decision rule restrictions only to a subset of the variables. And which subset, you might ask, right? So in that regard, just like we distinguish our constraints as state inequalities and the recourse constraints, let's do the same thing for our decision variables. So let's divide our decision variables as state variables and recourse variables. Again, using the very similar idea, state variables are going to be those that are linking our consecutive decision-making stages together. Recourse variables, on the other hand, they will be local to those stages. Once you make them, you move their information to the states and you forget about them. So in my production planning problem, recourse variables are how much I produce. State variables is the inventories that is sufficient for me to remember moving forward to inform my future decision-making. Right? So if you do that, for instance, both of them corresponding to stage T will appear in our recourse constraints, but in our state inequalities, basically these guys will be linking consecutive stages T and T minus 1. So our proposal is to apply these linear decision rule restrictions only to the state variables. And in this work, we are not restricting ourselves conceptually to just linear decision rules. You can apply your favorite decision rule, which could be linear, piecewise constant, quadratic, or anything nonlinear. It could be in the form of a neural network if you wish. So I'm going to compactly represent it in this general form of a decision rule, saying that this state variable vector associated with this stage T, which is a function of the history observed up until that point, of course, it is going to use the observation of the uncertainty, of course, up until that point. And then we will define these deterministic design parameters of the decision rule, which will be optimized as first stage decisions. So once more, I take my MSA problem. Now I distinguish my decision variables as the state ones, the blue ones, and the pink recourse ones. And we are only going to apply the decision rule restriction to our state variables, as a result of which we will not now collapse the multi-stage problem into one stage, but rather into a two-stage robust problem. So now in this collapse model, we have, of course, our original first stage variables. They remain in the first stage. And now we have our deterministic design parameters of the decision rules, betas, in the first stage. But once you make these decisions, x's and the betas, all of your future state variables are determined. But remember, these state variables were the only glue between your consecutive stages. Once you fix their values, there is no more link between the stages. So the rest of the problem, although you still have a T-stage problem, it decomposes, but there is no link between them. You can consider making all these decisions in one shot because you know their input state, output state. You just need to optimize them individually to decide what to do locally in between to go from the input state to the output state. So it becomes just everything combined. They become our second stage decision-making problem. So if we apply, in short, these so-called two-stage decision rules, we collapse our multi-stage robust problem into a two-stage adjustable robust optimization problem. So next question will be, of course, what to do. We want to solve this problem to get our most notable design parameters and describe a policy and eventually get an upper bound for our minimization error problem. So how can you solve this 2 error problem? It depends how this looks like, how this model looks like, right? So how are the coefficients? How is your uncertainty set? Whether you have purely continuous recourse in the second stage here or mixed integer. But what we propose here is the strength of this idea is we can borrow any one of you guys develop to solve the appropriate 2 error model. We can just plug in that technology to solve this to get a candidate policy for our multi-stage problem. So here I provided a very generic form of a decision rule for our state variables. Let me give you 2 instantiations of this as an example. So if you have continuous state variables, we can apply linear decision rules. In the next slide, I will tell you what we can do for bounded integer state variables. Combining these 2 ideas, you can actually design a decision rule for an example decision rule for mixed integer recourse problems. So if you have this state variable, this vector, which is purely continuous valued, so we can, as in the traditional case from the literature, we can actually restrict them via affine forms of uncertainty. So this generic form of decision rule, I can say it is basically a linear form of uncertainty. But there's a catch here. I put it still a little bit slightly more general than that. So these betas are, as before, they are deterministic. They are my regression coefficients, linear regression coefficients. But if you want to put this rule a bit more strength, you don't need to put, in the previous case, I put here psi t times beta t's. In other words, I put here the uncertain parameters as themselves, which are known to be standard basis functions. But if you like, you can do a little bit better and you can pre-design these objects that we are calling basis functions, which are going to map the uncertainty that is realized to you to a vector of numbers. So if you do that, for instance, instead of using, say, remember my example of linear regression was looking like this before, and I introduced these coefficients, and this was my linear decision rule or affine decision rule because this guy is 1. So now I can say, you know what, I don't want to use necessarily these guys as themselves. You can still use them, but I can also add some basis functions. But you can say, oh, I want to use a basis function which is multiplying the demand of stage 2 and 3. Or you can say the cube of the stage t demand, so on and so forth. So you can design your favorite basis functions and then have a little bit of more strength in your primal policy. So if you have, again, taking a step back, if we have continuous state variables, we can apply these linear decision rule forms. And then how can we solve this specific? Suppose you have an MSA with purely continuous state variables. You apply these linear decision rules to all of the state variables. You have your 2-stage arrow problem you obtained. How can you solve it? It, of course, depends how the second stage of this guy looks like. So recourse type matters, but also a bunch of other, of course, structural properties you might have. But if you don't want to worry about it, you want to employ some approximation methods by any means. For instance, we test computation a little bit k-adaptability. If you have a certain structure again, and if you want to solve this 2-arrow model exactly, CCG might be your friend. And I just would like to drop a couple of notes, which might be practically important to think about. I'm sure everyone is familiar, but specific to this 2-arrow model that we obtain for our multi-stage robust optimization problems, the first observation is if we apply linear decision rules, if we have all the continuous state variables and I apply linear decision rules, our master problem in the CCG is linear. We do not introduce any nonlinearity because of the LDRs, which is good. But depending upon the actual recourse type, it might be mixed integer still. But if you have purely continuous recourse, it is going to be just an LP, which is great. Subproblem could be computationally challenging to solve, but in certain cases that you are mostly familiar, I will say traditional assumptions, plus if you choose our basis functions specifically to be affine, so you don't have cube of something, if these are affine forms, if you choose them carefully, then actually subproblems in these cases, special cases, you can reformulate as a monolithic mixed integer linear program and give it to your favorite MIP solver. And CCG again under the traditional assumptions. And again, for instance, if you choose your basis functions in an affine form, it will have finite convergence guarantee. And for MSAOs with purely continuous recourse, just again, I will state the obvious, but this guy is if you were to consider the traditional approach from the literature and apply LDRs to all of the variables, this one is if you apply it to only our state variables, leave the recourse variables still free, flexible. Of course, we can obtain something better. We cannot do worse. But computationally, if you test these guys, this gap could be arbitrarily large, I would say. So this was for what you can do for continuous state variables. You can apply linear affine decision rules. What if you have integer state variables? And we look into the case where you have some or you derive some reasonable bound. So they are bounded integer state variables. So then we can propose, for instance, a piecewise constant rule for such state variables. So I'm not going to get into details, but what you need to do is suppose you have a specific, say, single ith variable, state variable, which is supposed to be integer valued between these lower bound and upper bound. So you can take these, say, kappa under bar +1 +2 up to the upper bar. So these are the possible values this state variable can take. You need to somehow create, it's a little bit like, if you will, like this uncertainty set partitioning type of thing. So we make up some region and we choose our, just like our basis functions, we choose some basis functions, if you will, and then we see where this basis function value takes you. And in this interval, if it takes you, so this is a partition of this -1, 1 interval, say this is my -1, 1 interval, say these are my regions. If this number takes you to this interval, you say, oh, this variable is going to be assigned to this particular integer value. But in order to ensure this, you need to, on your selected basis functions, have some certain conditions that are going to restrict the design variables betas. But in certain cases, you can really nicely, even in a linear fashion, reformulate these conditions needed via still robust optimization techniques. But anyway, so you can do, bottom line is, you can try for integer state variables, piecewise constant type of rules. How can you solve it? Again, looking at the structure in this model, you can borrow whatever amenable method you have from the literature, but similar cases that I mentioned earlier, CCG might be helpful. All right, so that was the primal side of the story. So it is, I would say, a bit more standard than the dual side. So dual side is gonna get a bit more interesting. So let me get to it right away. So let's again start simpler. Let's consider MSAOs with purely continuous recourse. We don't have any integer variables in our problem. So as we know, forget about multi-stage, stochastic, robust, whatnot. If you have any, say, LP problem, you have a primal model, we know that we have an associated dual model, for instance, LP dual, right? So if you have purely continuous decisions, just like this standard, I would say, LP duality, you can write the dual, just like LP dual, a dual of an MSAO model. So here, this is our MSAO model on the primal space, remember, where we had these functional form of the decisions. These are all like potentially infinitely dimensional objects themselves, but you can create similarly such infinite potential dimensional objects of dual variables, one corresponding to each constraint, and then you can write the dual of the MSAO problem. And this has been done in the literature. This has been proposed. This is known already. But then this guy is going to be difficult to solve because first and foremost, these guys, again, if you have infinitely many possible realizations of uncertainty, these are infinitely dimensional objects themselves. How can you solve this dual? You can get rid of that infinite dimensional concern of if their numbers are too big by applying a restriction on them. So for instance, if these guys, dual multipliers, they're of course continuous valued, you can apply linear decision rule restrictions on them so that you are going to define, remember my beta type of deterministic finitely many design LDR variables, linear regression coefficients, you can only optimize those. So this dual, it's going to give you for minimization problems, if this is minimization, it's going to give you a lower bound, but by restricting the dual decisions, you are not going to get the strongest lower bound, but you will get a valid lower bound. We have weak duality for sure. But in this approach where this duality game has been played, first of all, what they propose, it applies directly to stochastic programs. But you can use the similar idea for robust optimization problems. But as the user of this idea, you need to make up your favorite probability distribution. So you need to create or make up your probability distribution, which will have the support as the uncertainty set of the robust optimization problem. So in creating this dual problem, in order to transition from the primal to dual, you need to plug in your selected assigned probability distribution. So that's important. So this existing work, as I mentioned, it is considering the linear programming case. All the variables are continuous. Plus, you need to pick a probability distribution to derive the dual. And more importantly, the quality of the dual bound, it depends on the probability distribution. So there are two things. In the robust optimization setting, we don't know which distribution to use. And the quality has been observed to depend significantly on the chosen distribution. So there is an optimization of the distribution to be made. Plus, in this existing work, only continuous variables have been assumed. Accordingly, you use ideas mostly similar to LP duality, but we want to attack general mixed integer recurse MSA arrows. There is no LP concept here. So we use the next best thing you can think of as a dual. If you have a mixed integer problem, we can benefit from Lagrangian duality. So we want to use Lagrangian duality for MSA arrows. And again, this is an idea primarily rooted in stochastic programming. So we have, I'm not going to show you the whole so far, the MSA arrow right now, next slides maybe. But if you have such a problem, what is the Lagrangian dual? You pick a set of constraints that you identify, and then you introduce Lagrangian dual multipliers, lambdas on them, and then you push them into the objective, you dualize them. So then you have this Lagrangian relaxation problem, which is a function of these Lagrangian multipliers, and any favorite multipliers, non-negative you choose, you get a lower bound. And if you are looking for such strongest lower bound, you go ahead and optimize over this Lagrangian dual multiplier. So this is known to be the Lagrangian dual problem. So we want to employ this for MSA arrow problems. But the question is, fine, we are going to employ Lagrangian duality, but which formulation of MSA arrow we should apply it to? So the one that I showed you earlier on, we are not going to favor it because of what we observed in the stochastic programming literature. It is tending to be weaker than the next best thing we will consider. So we are going to instead first introduce this non-anticipative reformulation of the MSA arrow problem and do Lagrangian relaxation on top of this one. So it will bring us some more strength, but also potentially some computational advantages, if you will. So in order to create this reformulation of the original MSA arrow problem, I will first define a new set of new representation of our decisions. So we are calling them like these, if you will, perfect information variables. So this is a vector of variables, but note that this doesn't have a stage index. So this guy takes the whole sample path, all realization from our stage 1 to t as an input. And for one realization of uncertainty full sample path, this is going to tell you what to do at every stage. So this is a much larger vector, as you can imagine. So then using these variables, I will define where they will live. They will live in this capital Y space, again, parameterized by the whole sample path. Basically, you take their recurse constraints and corresponding state inequalities for that particular uncertainty realization, but for all stages. So now that I have these two objects at hand, I can reformulate my MSA arrow problem as follows. So remember, Z was our worst case total cost to be minimized, and it is going to be maximum of all the overall cost of overall the uncertainty realizations from our uncertainty set. So, but now here I'm plugging in our perfect information variables and their own spaces. But the important thing is, if we just consider this problem like this, there is nothing linking different uncertainty realizations, these guys. The only link that we need to enforce so that our model is exact, it's a correct reformulation, is the consistency between these perfect information variables. So these variables, they cheat. They anticipate the future, the whole sample path, and then they tell you what to do for that particular scenario, if you will. But we need to make them consistent. In other words, we need to make them non-anticipative. So we can do this. There are various ways to do it, but here I present pairwise way of making them non-anticipative, in other words, consistent. So for every stage t, give me two different sample paths, right? So maybe this one and this one. So then if at stage t you care, if these guys share the realizations history up until that t, these variables that are associated with stage t, they must be the same because they observe the same uncertainty up to t, although their future differs. They don't care. They only see the same information. They need to make the same decisions. So they need to be equal. So that's what this constraint is saying pairwise. So this is our reformulation, what we are calling non-anticipative reformulation of the MSERO problem. We are now gonna relax these constraints a la Lagrangian. That's the idea. So I brought them back here. So these are our non-anticipativity constraints, consistency constraints. So as I said, I want to relax these guys. I want to push them to the objective. Maybe let me clean it up. It's a bit crowded here. So I want to relax these constraints to the objective, but in order to do that, we first would like to scale these guys up. So what we want to do is we want to almost like multiply them with some kind of probability of that scenario. So we want to kind of scale these constraints for t and this guy with some probability number associated with that constraint. We are going to make up these numbers, and then we will scale them and then sum them up and then put them into the objective. So that's why here I am picking myself a probability distribution P. So where this distribution comes from, I'm going to make up some probabilities. Say maybe it's easier to think about discrete uncertainty set. Suppose you have a bunch of scenarios. You need to assign a probability number for each scenario from this discrete uncertainty set. And I am going to pick this distribution in such a way that the probability I assign to every scenario from my uncertainty set, it is strictly positive, so that I don't forget this constraint for that specific scenario. I care about them all. So if I choose such a probability distribution which assigns a positive density to every uncertainty realization in my support, then what we can show is for any such P, these constraints, we can reformulate them equivalently like this. So I'm not going to get into details, but this is saying now, this is not pairwise, right? This is for each T, only for only one uncertainty type. This is saying that what you should do for that specific scenario, it is kind of supposed to be equal to expected decision if you consider other scenarios that might happen. But expectation here, importantly, is taken with respect to the probability distribution that I picked. So what we do is, we do not relax these guys as is. We assign them a probability. We scale them accordingly. Scaling doesn't change anything because they are positive. And then when we put them into the objective in a summation manner, we show them, oh, actually, I can obtain equivalent reformulation, and I'm going to put this term into the objective. So then we consider this form of the non-anticipativity constraints. We dualize them in the Lagrangian framework. We get a Lagrangian relaxation problem. Say you are using gamma t, these Lagrangian dual multipliers to multiply each of these constraints to put them into the objective. But these guys, basically, then you can optimize, pick the best multipliers to obtain the so-called Lagrangian dual problem. So, but the important thing is this Lagrangian dual problem for our non-anticipativity formulation, it depends on the probability distribution we assign, we picked in getting this dual. And the quality of the bound that you will get from this dual, it heavily depends on this probability distribution you pick. But before I get to that one, just a quick comment is, if you have an MSERO problem with purely continuous recourse, it doesn't matter which probability distribution you pick. As long as you pick anybody from this set assigning a positive density to every realization, this dual, regardless of how you pick the P, which P you pick, it is exact. Just so you know. But otherwise, we need to first of all find the best P to pick. I'm going to get to that. But before that, these multipliers, Lagrangian dual multipliers, suppose this is a large set or this is an infinitely many dimensional set. These guys are also infinitely many dimensional. These are too difficult to work with. How we simplify them, as I've been telling all along during the talk, we restrict them by applying decision rules. So we take our Lagrangian dual multipliers. Instead of working with these functional objects, we introduce our linear regression, for instance, parameters, alphas, deterministic variables, and we pick our favorite basis functions of uncertainty, and we restrict the Lagrangian dual multipliers in this LDR form. And then instead of solving the original Lagrangian dual problem, we are going to solve the restricted problem, which is still a function of the probability distribution we picked. And the strength depends on the probability distribution. If you are looking for the best dual bound from this approach, then you also need to optimize the probability distribution you assign. And this is DRO-ish, but not per se DRO. This is what we are calling distribution optimization problem. You also need to optimize the probability distribution you pick so that you get the strongest dual bound. So from the dual side, basically, this is the model we advocate to solve if we can computationally by any means. And its objective value is corresponding to this DO version, restricted, and it is developed based on the non-speculative formulation. So there is one computational challenge to start with here is this probabilities. Suppose you have a discrete uncertainty set, right? You have a bunch of, say, 10 scenarios. You just need to decide which probability number to assign to each. But this is saying each probability should be strictly positive, which is not numerically favorable, right? It's not good. So we want to kind of make them greater than equal to. So we want to be okay to assign zero probability to some scenarios, if possible. And indeed, what we could show, which is not straightforward from the beginning, is if we allow our probability distributions to assign zero probability to some of the realizations, so that actually if you're assigning probability 0 to a realization, you do not work with the full support anymore. You only assume subset of the support is relevant to your problem. So if we allow our probability distribution to have some zero probabilities and instead solve this DO problem, distribution optimization problem, over those type of probability distributions to get this number, it's not obvious, but we can prove that this is still a valid lower bound on our true optimal objective value. So how does this DO problem looks like? I'm just going to give you the high level idea. This is a two-stage kind of a problem, or rather three-stage, if you will. So in this main part of the problem, this is the whole problem it looks like. We need to pick our decision rule parameters, linear regression parameters, to restrict the Lagrangian dual multipliers. And we need to have a model to choose this assigned probability distribution from this set, which we can nicely model. But then this objective here, the Q value, it is indeed an optimal value of a specific two-stage, not robust, stochastic program. So in order to handle this, if you want to design a cutting plane algorithm or whatnot, you can leverage some of the stochastic programming ideas. So the details of this model is not important, but one thing that I want to mention is in this two-stage stochastic program, the Z variable, the worst case cost variable, representation variable, it is the first stage variable. So these constraints do not simply decompose by uncertainty realization psi. They don't. They are linked together by the Z variable. Because we will have a version which decomposes in the next slide. So how do we solve this proposed dual DO problem? So we have, I'm not going to give you any details, just I will tell you what type of ideas we have. First of all, if you have a reasonable sized discrete uncertainty set, what we can do is, if your MSAO problem has purely continuous recourse, we show that this DO problem that we are trying to solve, it can be reformulated as a monolithic bilinear program. You can give it to Groby, for instance. If you have general mixed integer recourse, then we can solve it by means of a cutting plane algorithm. If you have either continuous uncertainty set or you have discrete but relatively large uncertainty set, then we employ the sampling idea. Instead of working with the full support, we get a subset of it, we sample, and then we play exactly the same game here just for the sample, and it is relatively easy to observe that exactly the same dual bound that we get for just the sampled version of the problem, it is a valid bound. So it's like you sample, meaning some of these non-unspecific constraints, when you sample some scenarios, uncertainty realizations, they don't show up, right, in your sample. It's like you give them a zero weight and you ignore them completely. So the sampled problem, we know for robust problem, it is a valid bound, and we get a further bound on the sampled bounding problem. The final methodological idea is, what if we have either we are in this case either continuous uncertainty set or a large discrete uncertainty set. Yes, we can play this sampling game, but when we go to this part, what we described so far, it doesn't have computational decomposability, which might be detrimental to the computational performance. If we could have decomposed it, it would have been better. So in that regard, we have another dual, which actually gives you that decomposability structure. So in that dual, we first need to start with an alternative version of the MS-Aero problem. It's exactly the same thing, except in the previous non-anticipative formulation of the original MS-Aero problem, I kept the z variable as is. So that's why that guy survived all along until the end as the linking first stage variable at the end of the DO problem. But if we could create a copy of that as well, perfect information version of this guy, and enforce non-anticipativity on the copies of this guy as well, we could also go ahead and relax these constraints, and then at the end, the obtained problem would have decomposability over uncertainty realizations psi. But of course, we are now weakening the problem because we are relaxing further. So we will get potentially weaker bounds, but because of decomposability over scenario uncertainty realizations, we will have computational benefits. And especially if you have continuous type of uncertainty sets, this could be very helpful because you can then use larger samples of scenarios to get these bounds. So I don't have much time left, so I'm just going to give you a high-level idea based on our preliminary computational experiments with these ideas. The primal bounds seem to be good, especially compared to the traditional LDR approach, where you restrict all of the variables for continuous recourse problems. The two-stage LDRs are very, very helpful. The dual bounds are looking promising. It seems to have some advantage over the known techniques, sampling-based bounds, perfect information bound, whatnot. And the decomposable dual has its benefits because of the special structure. So one example I had just as a proof of concept, but I guess in order to get some questions, I will just stop here by just concluding saying that what we propose is these like decision rule-based primal and dual bounding schemes, but because we collapsed the multi-stage problem into a two-stage problem, first, theoretically, we have much reduced complexity, but also we can truly leverage all of the methodological developments to solve two-stage ARO problems. I will stop here and thank you very much for your attention.